Hi, welcome to the first video in a series where we're going to look at electronics and electricity. Now, if you're a beginner, this is a great place to get started because we're going to be looking at electricity from the very basics all the way up to some pretty advanced applications. If you're an electrician or somebody who has a lot of experience already with electronics, I think there's still going to be a lot of stuff that you learn even about the basics as we get started learning about electricity. Now, to get started, the first thing that we really need to look at is what is electricity? We're not going to get overly technical about it because when you actually use electricity, a lot of the theory of how electrons move and how electricity actually works doesn't play in as much as you might think. So we'll look at this from a very general perspective. What is electricity? Well, electricity is simply electrons moving. Believe it or not, that's really what gets most of the work done when we turn on lights and run motors. It's really just the interaction of electrons. Now, inside of an atom, we have the protons and neutrons all in the center, but then all around the nucleus of the atom is a whole bunch of electrons. Now, depending on the type of material, which we'll talk about a little bit later when we get into what's called conductors, depending on the material, some allow electricity to move freely, others it's not quite so easy, and we lump those into different categories. If electricity can move freely, it's simply electrons move from one atom to the next atom to the next atom, kind of like the way a wave moves. Rather than a common analogy where we think about water flowing through a pipe, we'll actually return back to that and use that a lot later on, but rather than thinking about electrons as flowing through a wire, which is a pipe, they instead jump from one atom to the next atom to the next atom, a word that's called propagation. Like I said, just like the way waves move. Now, when we start looking at what it is that makes electricity move, one of the most basic terms that we refer to is called a circuit. Circuit sounds a lot like circle, and for good reason. A circuit consists of all of the required components and parts and pieces that we need to get electricity to move from one place to another while performing some sort of useful action. That's the whole point of a circuit. We want it to do something useful. So let's look today at the very first part that's absolutely required for a circuit to get something done, and that is the supply of power. Now, supplying power into a circuit, it can come from a lot of different ways. So we'll start with the most common ones. Probably the most common one is where we would plug something into a normal household outlet. You've seen these all the time. Every time we plug something in, cell phone charger, lamps, kitchen appliances, we're simply accessing electricity from a source that's somewhere else. And usually those sources come from hydroelectric dams, solar, wind. Most of the time, though, that energy comes from some sort of a magnet that's rotating inside a bunch of coils of wire, and that drives electricity. It's kind of interesting to think that so much of our electricity really just comes from magnets rotating. Hydroelectric, wind turbines, even nuclear and steam power plants are really just more extra ways to get a magnet to rotate inside a coil of wire and to do as efficiently as possible to generate as much electricity as possible. Now, since it's rotating, that electricity is constantly, due to the magnetic poles of north, south being rotated, that means that the electricity is also going to be going north, south, or as we call it in electricity, positive, negative, positive, negative. It alternates directions. So we call it alternating current. Now, there's a lot of different voltages. A lot of them are very unsafe, thousands, sometimes even millions of volts. That's what makes electricity travel through the wires outside. Once it gets down into your house, though, it's at a much safer level. Still not always safe. We have to be careful anytime we're dealing with electricity, but it's at a much safer level of about 120 volts. So we would call these outlets, at least in the US, 120 volt alternating current AC outlets. Now, that speed at which it's going back and forth is a frequency of rotation. I call it a hertz. 60 hertz electricity. In many other parts of the world, it's 50 hertz. And that just refers to how fast those generators are rotating their magnets inside that magnetic field to allow that electricity to be generated. But because of this constant push, pull, we never see what's called the plus or minus like we do when we pull out a battery. And we'll look at batteries in a minute. Those always have a plus and a minus. Well, alternating current doesn't really have a plus or a minus because it's constantly changing directions. So instead, we have to simply say it's going to deliver energy to a source, sometimes pushing the electrons, sometimes pulling the electrons, but for a lot of devices that doesn't really matter. If we're heating up something in a stove or a griddle, we can pull electrons or push electrons, and we're still going to heat up that element. So we don't have to do anything fancy to it. Same with some light bulbs. We can send electricity in or pull electricity or back and forth, and it really doesn't change that the light bulb is going to give off light. So we don't have to do anything to that electricity in order to get it to accomplish its task. When we plug something into an outlet, usually that's going to be through the 3-prong outlet connector, kind of like when you plug in a computer, laptop charger, or usually cell phone chargers sometimes won't have this third one, which is a grounding plug. Later on, we'll talk about what grounding is. It's very important in a lot of applications, but at least as far as supplying electricity, that ground isn't really necessary. Instead, we have 2 other plugs. Now, have you ever noticed that in some plugs, one of them is bigger than the other? Polarity of a connection, when we think about batteries, we think of plus and minus, kind of like polarity, poles, north, south. It all comes back to that direction of electricity flow. The 2 different sizes refer to which one of the plugs is the one actually supplying the energy that's required to push or pull. The other one is simply the return path. The one that's providing the energy push-pull we refer to as the hot or the live wire. And so in wiring, we might see this as an L. Line, live, and hot is another really common way to refer to that. The other one is the neutral. That also comes in when we look at the wire colors. Now green is that third ground one. Again, we'll talk about that later. But black and white. Black is the hot wire. Not to be confused with a lot of times when we deal with batteries, like this one, we have a black and a red wire. The black on DC has a different application. We'll talk about that in a minute. It comes a little bit further down the road. Black is the wire that supplies the energy to give us the push-pull. White is simply the return path that either provides the electrons or lets the electrons flow back. It's all part of this big supply circuit that really feeds all the way back to those hydroelectric power plants and substations that do all the energy changing of different voltages. When we look at an outlet, see on one side of the outlet there's silver screws. On another side of the outlet there are gold screws. And down here at the end there's a green one. The green is pretty straightforward. That's the ground. The other 2 sides, the silver connects to the white neutral wire, and the brass gold topped screws, those connect to the hot or live wire. So if we look at the sides that match up with that, the small side is the one that provides the energy. The big side of the outlet is the one that's simply the return path. Now the reason they choose that, big and small, is that it's easier to accidentally or on purpose, you gotta be careful, it's easier to stick something into a bigger plug outlet than into a smaller one. So if we plug something on accident into the bigger one, it would probably be better if that bigger one was the return path, and the one that's the hardest to accidentally stick a pair of tweezers or a fork or something into, the smaller one is the one that actually supplies the energy, the live wire. Now that doesn't mean we don't have to be careful, obviously. You can still stick tweezers into something that's even the smaller one. But it does make it a little bit more difficult when one is smaller. So that's why a lot of the plugs that you see, one of them is bigger than the other. Now sometimes we'll just have 2 prongs at the end and they're exactly the same size. Like most lamps and floor standing lamps, and a lot of cell phone chargers, you can plug those in either direction. And the reason for that is that when we change things into direct current, instead of alternating, it all goes in one specific direction. When they're the same size, the electricity is able to change from the negative direction into all of it being in one direction. It doesn't matter which one was supplying the power or the return path, they'll both end up supplying electricity in the same direction. So in those cases, we can plug that outlet in either way, doesn't make any difference. Now that's at least the basics of our small voltage alternating current. There's also a whole nother level of alternating electricity that instead of consisting of these 2 wires, one to supply the energy and one to give it a return path, is 3 coordinated, all working together wires that all supply energy. We refer to that as 3-phase electricity rather than 1 phase and the return path. Now in three-phase electricity, often the one that's providing the power in one direction, there will be another one that's providing a negative power in the other direction. So we often don't even have that neutral return wire. We simply have three energy supplying wires that'll all work in coordination with each other to get the job done. Three-phase electricity can deliver power through three wires instead of just one wire, so we can use much smaller wires if the stuff that we're needing to drive is these huge devices, like giant motors. You don't have any of those in your house, so that's why three-phase electricity isn't really common to see in any household applications. Sometimes you'll see it in a shop or a barn if there's big machinery running, but most of the time, those just stay in industrial facilities. Three-phase supplies are extremely common when there's big motors running in lumber mills or processing plants, manufacturing warehouses. We see that all the time, but it's a little less common to see in our everyday applications. These small wall outlets, these kind of things, they're common all over the place in every single shop, house. So we see these all the time. Now, the other method of using electricity doesn't come from this alternating current where it comes out of a wall outlet with basically it never really runs out. So we could kind of think about it like this infinite well of energy. Other times, we only have a finite amount of electricity to use. That's when things can get a little bit trickier. That usually comes in the form of a battery. Now, batteries can range anything from big, huge car batteries all the way down to the tiny little hearing aid batteries, but every one of them is designed for a very specific application. Now, when it comes to batteries, there's three main numbers that we need to deal with. But usually only one of them is really easy to locate and to easily measure. The other two, we have to know a little bit more about why a battery works the way it does in order to find out how much it's going to do or whether it's going to be correct for an application. So that easiest number to deal with is the voltage of the battery. Almost always when we talk about a battery, the volts of the battery are something that we talk about right along with. I mean, a 9-volt battery. We know exactly what a 9-volt battery looks like. When we talk about a 9-volt battery, we're talking about the voltage. It's a really easy number to know. Now, some other batteries, here I've got a AA and a AAA battery. That's not quite so much stated as far as what the voltage is, but if we take a close look on it, we're probably going to see that it says AA 1.5 volts. So this is a 1.5 volt battery. Here's a AAA. I'm looking for the voltage on a AAA, and here it is, 1.5 volts. So a AA and a AAA are both the same voltage. That's kind of interesting because they're whole different sizes. Here's another one. You got a D battery, 1.5 volts. So we're saying that a AAA has the same voltage as a D battery, and that's correct. The voltage is a really important number to know, but sometimes it's a little bit misleading. We often think, well, it's a bigger battery. It can do more work. Maybe it can, but if we just look at the voltage, that can be pretty misleading. Here's another common kind of battery. If you've ever torn apart a computer, those are very often the little motherboard batteries. So sometimes I call them coin cell batteries. Often kids' toys will have those little LR44 batteries that are super hard to find. And they always take like 18 of these tiny little batteries, and all they do is just make noise. Anyway, I've got lots of those at home. This coin cell battery looks really tiny when we compare it to a D battery. So one would think, you think by looking at it, well, this one can obviously do a whole lot more than this one can. But if I look at the volts on top of it, this says 3 volts. This is only 1.5 volts. That's kind of odd. Twice the voltage coming from this little battery than this huge one. Well, I guess that's another kind of an interesting thing when we look at the 9-volt battery. A 9-volt battery, 1.5 volts. That means it's 6 times more voltage in this battery than this battery, but it's smaller. Now, car batteries are 12 volts. So those ones have even more voltage. But the size of that lead acid huge car or truck battery, those things are huge. And you're saying that they're only 3 volts more than a 9-volt battery? 9, 10, 11, 12. So really, this 9 and 3-volt battery stuck together has the same amount of voltage as a car battery? So why can't I run my car off of something like this, and when my battery goes out, replace it with this instead of replacing it with a $100, $150 interstate battery? What's the difference? Well, that's another interesting property that we need to look at in batteries, since they are not an infinite supply of energy, like we kind of think about a wall outlet. We have to think about how much capacity the battery has. Voltage is the amount of force that's required to drive electrons, but it does not refer to how much electricity it can deliver. Electricity, when we think about the supply of electricity, that voltage number is really only about the application of pressure. When electricity is dealt with, we can think about it in a lot of ways like a water system. Water flows through pipes, and in your house, there's a certain amount of pressure. Now, the amount of pressure is usually around 40 to 60 psi, and it's going to be the same pressure no matter whether it's supplying water into the washing machine or coming out of a faucet when you turn it on. They all have the same amount of pressure. Now, pressure can be developed even if there's not a lot of water flowing. In fact, pressure can be developed even if there's no water flowing. Whether you have a well and the pump is supplying the amount of pressure, or it's a city water system and a water tower or another type of delivery system is supplying the pressure, that pressure is only referring to how much water could be pressed, how hard we could press on the water going into it. It doesn't actually mean that anything's happening. So sometimes in electricity, instead of referring to water pressure as the voltage, which it is, we can refer to it instead as potential. So sometimes voltage is referred to as a potential. It doesn't mean that something's happening. It means that something could happen if we give it a circuit to work with. This application of power at the beginning is only the first thing that's required for a circuit, but it doesn't mean that something is happening. This battery has 1.5 volts of pressure, of amount of ability to potentially drive electricity right now, and it'll also have that same 1.5 volts if I hook a wire to it and allow it to complete the circuit. Or I hook it to a little light bulb or a tiny little motor. It still has the same amount of potential to deliver energy. But how much energy can it deliver? That's a really good question. The amount of energy that can be delivered from a battery is only a limited amount. The battery's gonna run out after a while. That's a little bit more when we look at the size of a battery. This isn't universally the case. There's different types of batteries, but for the most part, if you see two batteries, the bigger one can probably deliver more energy than the smaller one. Now, there's a lot of variables behind that. There's a lot of different structures of batteries and chemical compositions inside, and that is true. They're not all the same. But most of the time, a huge battery is going to have a bigger storage of energy inside of it than a small one. That's the reason why the car battery has to be so big to deliver all of the energy that's required to drive the spark plugs and drive your headlights and all the electronics inside the car. And this setup of a 9 volt plus a little 3 volt battery is never going to be able to supply that amount of energy. Two reasons. First, it's going to run out really fast. The capacity of a battery is usually what we refer to as milliamp hours, or if it's a huge battery, sometimes amp hours. Now, the amp hours of a battery, if we use a battery for 1 hour and we use 1 amp, which is quite a bit of electricity actually, if we use 1 amp for 1 hour and then the battery's dead, we would say that that battery has 1 amp hour. Well, that means if we only need half of an amp, it should last for 2 hours. So if we take the amount of energy that we can get out of the battery, or the amount of current that we can get out of the battery, multiplied by the amount of time that the battery is going to last for, that means we can either use a little bit of energy and have it last for a long time, or we could use a lot of energy and it's going to go dead really fast. That capacity in milliamp hours is not always written right on the battery. Sometimes it is, and sometimes we'll see numbers, especially when it's a rechargeable battery, we might see something like 1800 mAh, a little lowercase m-a-h. That stands for milliamp hours. So if it's 1800 or 2000 or 2500 milliamp hours, divide that number by 1,000, so 2500 would be 2.5 amp hours. I could use 2.5 amps from that battery for 1 hour, Or I could use much less current, much less amps, for a much longer period of time. So we really just have to decide, what is the thing that we're trying to drive? Is it going to use a lot of energy, or is it only going to use a little bit of energy over that long period of time? Do I need to supply a ton of energy to something for a very short time, or a small amount of energy for a very, very long time? Now, another reason why one battery might be more appropriate than the other kind of has to do with that whole delivering energy. And just to say, well, this might be 100 or 1,000 milliamp hours. Well, I can use 1 amp for 1 hour. True, but that little battery may not be able to supply 1 amp. That may not be capable of sending you 1 whole amp of current. So another concept that's even more difficult than the idea of capacity in milliamp hours, the other thing is what they call internal resistance of a battery. The internal resistance has to do with the chemical combination that's driving the electricity out of that battery. And if it has a very low internal resistance, that means it can supply a lot of current. But if it has a very high internal resistance, it can only supply a little bit of current. Most types of batteries, there's only a few different types of construction of batteries, and being able to place the little cells of chemical combinations that drive electricity, if we can stack a whole bunch of them end to end with each other, we call that series. We can drive a lot of pressure or voltage, but with not a whole lot of flow. But if we stick those little cells a whole bunch side by side with each other, we haven't developed a whole lot of pressure, so it's still only a small amount of voltage, but a whole bunch side by side all together can supply more electricity or more current. So if they're all side by side, the voltage is low, but the internal resistance is also low. We can supply a lot more energy. If we stack them all up end to end, which is series, we can supply a lot of voltage, but our internal resistance has gone way up, so we can't supply a whole lot of current. Now, if we take a whole bunch of those series with high voltage and stick a whole bunch of those side by side, now we get a lot more voltage and a lot more current, which means a very low internal resistance. But as you can imagine, sticking a whole bunch in series and parallel is going to lead to a big battery. That's why the car battery is so big. That car battery can supply 12 volts, which is a pretty good amount of voltage when you compare it to 1.5. But its internal resistance is so incredibly low that it can supply a ton of current. How much current? Well, if you look at the top of it, there's a little thing that says CA and CCA. That stands for cranking and cold cranking amps. Those can be in the hundreds, sometimes even more than 1,000. Hundreds of amps of current able to be supplied from a car battery. That is a lot of current, which means that although working on a car battery is not dangerous from the voltage sense, it won't hurt you to work on it. If you get a wire in the wrong place, it can definitely damage that wire. Incorrectly wiring things up to cars or dropping tools across car battery terminals, when you can supply 600, 800, or even 1,000 amps, you can do a lot of damage, even melting little wrenches and tiny wires. You'll watch the insulation dripping off of those. Done that many times myself. Sometimes it's a little difficult to know exactly where to connect this wire to safely, and make one mistake, and that wire is going to get really hot really fast. But if we do that same thing with, say, a 9-volt battery, that's almost as much voltage as a 12-volt battery in your car. But if we took a piece of wire, in fact, this happened to me a while ago. I was carrying the 9-volt battery in my pocket, and the keys, my key ring, touched across both of the terminals, just like a wrench touching across it. Now, did it melt that key ring? No, didn't get nearly that hot, but it got warm enough that I said, something's weird in my pocket. There's something hot. I had touched metal across both terminals of that battery. So it will heat up for sure, but it's not going to melt a giant piece of metal like a car battery would. Now, some kinds of batteries, this one is they call it a lithium battery, lithium polymer battery. These ones are really common to see in drones and other things that have motors in them because motors require a lot more current. If it's just a little kid's toy that has lights, maybe a speaker that makes some noise, they can get away with really small batteries because those don't require a whole lot of current. They require some voltage, and we know that we can get voltage from pretty much any battery, but current is really going to be, it's really going to change depending on what kind of battery we choose. So lights and motors really, lights and speakers really don't require that much energy. But in a drone, we're having to drive motors, brushless motors, at a really high speed. We're gonna have to have some pretty special batteries for that. So this one here, this is a lithium polymer battery. And if we look at the front of it, it says 3.7 volts. 3.7, that's not really a whole lot. That's only a couple of AA batteries, a little over a couple of AA batteries stuck end to end with each other. 3.7, 1200 milliamp hours. 1200 milliamp hours. I mean, I've seen AA batteries that have twice that. AA battery, 2 times the amount of storage space of this battery. So why is this thing so good? If I could just take a couple of AA batteries instead of this thing that I'm going to have to special order from somewhere. I can't pick this up in Walmart, but these, they're everywhere. So why could I not use a couple of these, which have more storage capacity and could get the same amount of voltage as this thing? What's so special? The special thing is the internal resistance, which on these is extremely low, which means I can grab a lot of current to drive those motors out of this battery. But that also means it's going to go dead a whole lot faster. So when we're flying a drone, you'll notice that you only get a little bit of flight time out of those before you have to change the batteries. So the batteries won't always look like this. Sometimes you buy them and they'll have a little plastic package around it, but it's pretty much one of these inside of it. It can deliver a lot of current because it has an extremely low internal resistance, even though the voltage is only 3.7, fairly low voltage, and a 1200 milliamp hour, which really isn't all that special. That's not a huge amount of capacity, but the ability to deliver a lot of current very quickly is what makes these so special. Since they can deliver a lot of current, you got to treat them kind of like that car battery. Don't touch metal across the 2 terminals. That's why they always come with a special connector. You can't get it wrong. You don't pull that connector off and touch those wires together. I've seen some of these that are so, they can deliver so much current that you accidentally, working with 2 bare wires, you get those a little too close and a spark jumps across and instantly those 2 are welded together and the whole battery starts burning or even exploding. That's not a joke with these things. They are extremely dangerous if not handled properly, even though the voltage and capacity seem really low. That internal resistance is a really big deal when it comes to batteries. Now we can get 12 volts from the car battery. You've all seen things that use the car adapters with, maybe it's a cell phone charger, maybe it's the little USB connector on the end, but it is only 12 volts, and usually they're limited in the amount of electricity that they can supply. This one here is a car charger that says output 12 volts, 1.5 amps. So it's a fairly decent amount, but that's not a huge amount. We got to be careful that the stuff that we connect to it, which will come in a later video when we talk about load devices, those are a very important characteristic of our circuits. That load device is going to determine how much electricity or how much current we're using. Don't connect the wrong load devices, or else we can ask for too much electricity and we can start burning up the components inside of this thing. Since the battery from the car can supply a lot, if we ask for it, it's going to try to deliver that much. And if something inside here is the weak point, maybe that's the wires, maybe that's some components or chips inside, if those are the weak point, they will start melting or catching on fire. And then smoke starts coming out and the device is destroyed. Now, when it comes to voltages that are safe and unsafe, usually, now, again, I want to stress that if you mishandle voltage, it can be dangerous. And it really doesn't matter what that voltage is. Even a couple of volts can be dangerous to either you or devices that you're dealing with. But usually the line where we say above this voltage, something is extremely dangerous, below this voltage is something that is probably not dangerous to a person, is around 50 volts. So if DC 12 volts and the 1.5 volt batteries, those aren't going to hurt a person when they come in contact with them, but they can certainly hurt the devices being connected to them. If it's over 50 volts, like your wall outlet at 120 volts, that certainly can be dangerous, and it's not something that we just want to play around with unless we really know what we're doing. Now, I don't say that in order to say be scared of electricity, but as with anything, if it can be dangerous, we probably want to just respect it. That's the way everything works. As long as you understand it, electricity works in a very consistent, very methodical manner. And so as long as you understand it, you can do some pretty amazing things with electricity. We just have to don't get careless with it, or we have to remember it can cause problems. Now, one thing that kind of puts these two together, there's the batteries that deal with the direct current, where all the electricity goes from a plus to a minus. And in fact, when you look at a battery, here's a minus, there's a plus. Here's another battery, there's a plus. Minus isn't always marked, but almost every battery we look at, there's a plus. The plus and minus will always be marked because it has a specific direction we have to plug stuff in. Alternating current is not so. In devices like these, where we have this, what they call a barrel connector, you've seen these before. Some cell phones used to be charged this way. Very rarely see that anymore, but this came from a little portable DVD player. So we still see this kind of thing all the time. This little marking on the tag, you see that little thing? It has a little plus and a minus right there. That little plus and minus refer to which of these, is it the metal that I can see here, or is it the metal that's inside? Which one is the plus and minus? Most of the time, and this is the case, you see the plus is connected to the little dot that goes to the center. They call that center positive, which means the outside, right here, the line that's connected, there's the minus sign, and it goes to the line that's kind of forming that C shape on the outside around it. That means that the outside of this is ground. That's usually the case because if I plug this in, what do I want to be able to touch? Do I want to be able to touch the live voltage and accidentally connect it to something metal? Or the ground, which if I touch something metal, it's already grounded, it's not going to hurt anything. Well, obviously, I want to make sure it's as safe as possible. So most of the time means that there's always some exceptions to that. But if you see a little tag like that, you'll almost always see the center as being positive and the outside is negative, but we always want to check with that to make sure. There's another classification of power supplies that put both of these together, and it's ones where we can plug it into a wall or permanently wire it up. Doesn't always plug into a normal outlet, but we supply AC electricity into it from that nearly infinite source of electricity that comes out of your walls, and we get DC out of it. That's really common as well. Every cell phone charger, you plug it into the wall, you're putting in AC, you're getting out DC, and usually cell phone chargers are 5 volts DC. But this is another kind of device. Most likely, unless you've worked in the industry, you've probably never seen something like a 24 volt power supply. This is a pretty big chunky device. It does not plug in directly into a wall. Instead, it has what's called L, in, and sometimes this little protective ground connection. Like I said, we'll talk about ground sometime later, but see L and in, line, or live, neutral. Those go back to those AC words that we were talking about before. 50, 60 hertz, 100 to 240 VAC uses 1.15 amps. So it's told us a lot of information that we need to know about that. Now up here on the other side, it says V plus and V minus. That's the positive and negative, just like we see from a battery. So we now know exactly how to connect this to all the devices that are going to use this D24 24 volt power supply. That's something that we'll have whole content on later on, because although it's not common to see that all the time in your house, it's extremely common to see 24 volts out in industry. And those circuits can get really fun. They're a little more unusual, but they can do some pretty amazing stuff with industrial control devices. So we'll be getting into that quite a bit. But for now, we just have to be aware that sometimes there's some big beefy power supplies that output DC when you put in AC. Everything from the little cell phone chargers all the way up to big power supplies like this and ones like found inside of a computer. Those output DC when you supply AC. There's different words for that, but usually we simply call it a DC power supply in comparison or in contrast to the battery, which is a DC power supply, but we just call that a battery. The AC power supply, we don't really have to call it a power supply, because if we just had an AC supply, we don't have to do anything fancy to that AC supply. We just plug something into the wall and we've got AC. But that AC can again be either our normal one line and then the neutral return path, which is a single phase. Just that black wire is the only phase in that line. And we call that single phase electricity. 120, 60 hertz, single phase, that's our normal outlet. But we can also have three-phase electricity, which is three current-carrying wires that deliver energy, all working in coordination with each other, and often no return path because the other current-carrying wires are the return path. So we have three phases of electricity, and that's really common in industry. So later on, we're going to be going from talking about the supplying of power, and the other critical components that we're going to have to look at next in the next few videos are going to be the current carrying capacity of the circuit. The circuit's got to have wires or something to carry the electricity, or it's not a circuit. You can't have power alone with no path and anywhere for it to go. And we also have to look at what's the device that's using the electricity. If we just took a battery and wrapped a wire around it, well, that's where the explosions happen. That's the wrench being dropped across it. We must have something else in there to keep that from happening. So we call those the load devices. So we've talked about the power supply. Next, we're going to talk about the conductors, and that's allowing current to flow through the wires. And we've got to talk about the load devices. Now, there's another device that we'll talk a lot about. Technically, it's not required for a circuit, but you're going to see it everywhere anyway, and that's the control devices, like a light switch. I can't imagine having a light that's just on always. We got a switch to turn it on and off somewhere, and almost everything has an on-off switch somewhere. That must mean that it's very common to have a control device plugged into the circuit. So that's, in summary, these four basic requirements for a circuit to deliver electricity to get something accomplished. The power supply, which we've looked at now, the conductors that give us a path for electricity to flow, the load device, which actually uses the electricity and does the thing that we want it to do, and the control devices that make sure that we choose when it's doing that thing that it's supposed to do. So we're going to spend a lot of time looking at electronics. And whether you're brand new to this or experienced, there's probably going to be a lot of new stuff that we can learn and see about electricity to make sure that we understand exactly why it works and that we really don't have to be afraid of electricity in any way, as long as we just know to respect it. So as always, if you have any questions, feel free to message me, comment on the video, and let me know if there's specific things that you want to know, and I can either design extra videos or just answer your question, because I love this stuff. It's really exciting, and I'm always willing to learn more, and honestly, finding out new resources and researching new things is really what gives me a lot of enjoyment about electricity. Even though it's consistent, there's always new things to learn. So I'll provide you with some resources and some helpful links that you can use to do a little bit of research on your own. And then as you follow through more of these videos, hopefully that will increase your understanding of electricity and show you some pretty amazing things that you can do with it. So bye for now, but I hope to see you again soon with future videos. Take care.